So my first question is related to indoor solar cells only. So can you provide an overview of your manufacturing process for indoor solar cells and also the unique feature compared to the traditional photovoltaic cells?
So what we're working with at Epishine is organic solar cells, and the organic comes from that the active layer is composed of hydrocarbons. So basically, long polymer chains is the main component of the active layer. All materials when we build our solar cells, which is sort of based like a sandwich, you have your electrodes laterally transporting current in the solar cell. You have your active layer, this polymer-based converting light energy into electrical energy, and then you have some interlayers making sure to guide your current the right way in the solar cell. All of these layers we deposit from solutions, so we're using printing and coating methods in a roll-to-roll process. Mainly, I would say screen printing and slot die coating to print the solar cell and also connectors out to the outside world to be able to harness the electric power. And then we also have developed a conversion process. I would say what sort of makes Epishine a bit unique compared to other organic solar cell manufacturers is that we have developed a lamination method where we coat half the solar cell on one substrate. So basically you have your electrode and active layer on one PET substrate, the other electrode and active layer on another PET substrate, and then we use heat and pressure to laminate these two together, and this way we can get a really high yield and robust performance at low light intensities. And compared to what you have seen before for indoor solar cells, it's basically a more silicon that's been around for a while. For instance, in the pocket calculators since quite a long time back, and there what we can then do with our technology is that we can enable a more robust and higher performance compared to these ones.
Okay. So you're saying that your solar cells are unique in that way. Okay.
Yep.
So how does your technology capture and convert indoor light into electrical energy? And what is the basic technology involved, the technical principle behind that?
So it's the photovoltaic effect. It's solar cells, but instead of putting them under the sun, we put them under LED or fluorescent light sources indoors. So basically, the light intensity or light flux hitting the solar cell is maybe a factor of 100 or 1,000 lower compared to the light intensities outdoors. And this means that you, number one, need to make sure that you absorb the visible light, because for instance, a silicon solar cell is designed to absorb quite much of the near infrared light, also to get a lot of photocurrent out of the solar cell. Indoors, it's enough to absorb whatever is in the visible region, because this is typically where the light sources emit light. And what is also super critical for indoor applications is that you have a really high parallel resistance in your solar cell, and this means that you basically avoid any short circuits, because at really low light intensities, if you have small short circuits or a lower parallel resistance, you will get a much lower performance out of your solar cell. So quite similar to standard solar cells for outdoor applications, but you really need to have a high parallel resistance. I would say this is one of the keys.
So is there any technical innovation or any feature that differentiate your cells in terms of capturing and converting indoor light?
Yeah, I would say, like I referred to before here, this lamination method that we have developed, which allows us to have a really high parallel resistance, or basically avoiding shunts, because this gives a really reliable performance of our solar cell and a high yield in our production process.
Okay, so can you elaborate on this method, sir, that how it works?
Yeah, absolutely. So typically you have your substrate, and for printed PV, that's typically a PET foil somewhere between 50 and 150 micron, and on top of this you then from solution you coat or print your first layer from solution, you put it into an oven, you dry out the solvent, and then you build a stack, you put on the next wet film, you dry it out, put on the next film, etc. And then for organic solar cells, the semiconductor, the active layer, is typically 100 or a couple of 100 nanometers thin or thick, depending on how you view it, compared to a human hair. It's a factor of 1,000 less in thickness. So these are super thin layers, meaning that when you try to coat this over large areas, it's a quite high risk that you get small local de-wettings or small pinholes in this film. Can be from small dust particles, it can be from irregularities in your substrate, it can be from small particles, aggregates in your ink, many different sources. And if you get this, you will get a local de-wetting, and basically there you risk to get a contact between your top and your bottom electrode. If you work in outdoor applications, this is not so sensitive. You can live with a little bit of this, but as soon as you move into indoor light and you have a lot less light intensities, you become very much more sensitive to this. And then what we have developed at Epishine is that you then have your substrate with half the solar cell coated and all the layers are dry, the other substrate with half of the thin film stack, all layers are dry, and then in the dry state we use heat and pressure to laminate these ones together, and this way we can avoid that you get any contact between the electrodes through the active layer, because you have no liquid that sort of fills the cavities. Worst case is that you get sort of two small voids overlapping, but there is no conductive material in between. So this way we can avoid shunts and thereby allow for a really high parallel resistance in the devices. And this in turn then leads to a robust indoor performance.
Okay.
Reproducible and high, yeah.
Okay, so what measures have you taken to improve their efficiency in
to
low light
improve the
conditions?
efficiency under
In low light conditions.
Yeah. Focus has been very much to get our product out on the market, and we're working with organic solar cells. And today the active layer is based on a conjugated polymer that's mixed with a small carbon molecule called fullerenes. It's like small carbon footballs with a functional tail on it to make sure you can dissolve them. And this is allowing for a good performance, but what we also are working on now within our R&D team is to exchange these fullerenes for other type of small molecules, and there we will be able hopefully to double the power conversion efficiency of our solar cells, basically by changing a few of the components then in the active layer of the solar cells. These are called non-fullerene acceptors in the academic field, and this is of course also where we're trying to push to be able to improve the power conversion efficiency.
Okay, so in terms of material science engineering, how the organic photovoltaic innovation is different from the solar cell technologies, and how this innovation benefit IoT applications?
How the innovation benefit IoT applications is that you have a new technology where we see that we have a really high and robust performance. And if you look at indoor applications for IoT products, if you use them in indoor applications, typically the light intensity vary quite much. So if you know that you can trust the minimum performance of your solar cell, then the only thing you need to consider is then the light intensity variations, depending on where you place your sample, for instance. Other aspects with our solar cell I think can be beneficial is that they are really low weight. The total thickness is 0.2 millimeters or 200 micron. They have a quite low environmental impact comparably, and are lightweight and fairly then easy to integrate.
So what material are used in your manufacturing process, and how do they contribute to the efficiency and scalability of your product?
The substrates we are using is PET, and that's typically, I said the thickness of the solar cell is 200. I think it's actually maybe 210 micron. PT constitute about 200 micron of this, and the solar cell is less than a micrometer in total. For the solar cell material, it's basically conjugated organic molecules, and the rest is PET, if you look at sort of the main components. And then there is a small silver print on the side to conduct the current from the solar cell out to the contacts.
Okay. So how have you optimized your manufacturing process to ensure consistent quality and high yield?
Yeah, very good question. Of course, this is a challenge. It takes time, and I think it's super fun and of course also frustrating to really take a technology into a volume manufacturing. But what we see is that when we move from making a lot of things sort of in the lab with hands up, and then using this roll-to-roll method, the reproducibility has increased a lot, and that's been a really nice thing to see. So very much about the calibration, making sure that we have the same pressures, temperatures everywhere, of course, in the manufacturing. Year ago, I think we also made a bit of efforts to work on the dust levels, especially in the vicinity then of the wet layers, for example. But then we also been working in close relationship with machine manufacturers. So it's sort of standard components for the machines that we are working with, but we are then assembling them in a, for us, quite unique way. And then also when you have this lamination process, you get a lot of challenges in terms of the tolerances to make sure that you align your foils. And there we have done quite substantial works as well then to make sure that you get a robust process in that perspective.
So what is the current production capacity of your indoor solar cell, and how do you plan to scale it up with the growing market demand?
I think the nice thing with a roll-to-roll manufacturing process is that it sort of by default allows you to have a huge capacity. So right now, we typically say that we have the capacity that's required from our customers, so we can meet sort of the deliveries that delivery expectations they have on us.
So how do you ensure efficient utilization of resources and minimize waste during manufacturing process?
Very good question. I think this is something that both from an environmental perspective and from a cost perspective is super important. So I mean, for roll-to-roll production, you have what you refer to as your head and tail to be sort of able to align this. This is something we try to reduce, and especially if you go for longer rolls, by default, you then get a shorter head and tail, which then would become waste in the foil. Also trying to make sure that we adapt sort of the product sizes and the mother roll materials to fit as well as possible. But in general, I would say that the longer rolls you make, the lower the waste is, and the more efficient you utilize your resources to have as a sort of simple metric.
So are there any eco-friendly or sustainable particles integrated into your manufacturing operation?
I mean, if we performed a life cycle assessment on our manufacturing process and the product together with a consultancy company experts in this, and this showed us, I don't quote me exact for the numbers, but I think it's like 37 grams carbon dioxide equivalents per standard component, which is a 50 by 50 square millimeter device we have. And to our knowledge, this is a really good and really low environmental impact for a solar cell material, although you shouldn't compare this to outdoor solar cells, of course, because this is then optimized for indoor applications. So
what quality control process and testing methods do you employ to ensure the reliability and performance of your indoor solar cells?
We have inspection cameras in the machine that look for visual defects and for instance missing glue, etc. We also do electrical tests, IV sweeps for all of our modules to make sure that they perform as they should. And then we do accelerated aging. I mean, we sample from all production batches we run. We sample batches for accelerated aging, can be damp heat in climate chambers, also dark heat ovens, light soaking, etc., to make sure that each batch is sort of quality tested in that way as well.
So can you share any result or data from performed testing in real world indoor environments?
I mean, the sort of what we get out of the machines, depending on how you then normalize and what measures you take. Indoor solar cell measurements are still not really in a stage where you really can compare between labs or between factories. But I would say somewhere between 20 and 22 microwatts per square centimeter at 500 lux illumination, and that's LED. So typically that is the light intensity maybe you have in an office. And then 1 square centimeter of solar cell, you can get somewhere between 20 and 22 microwatts of electric power out of your device. And then we have a number of collaborations and a number of products out on the market. For instance, a temperature and humidity sensor with a Swedish company called Elsys. Few more products there also, and I think this is more Jesper's area, so maybe you can fill out a bit more here.
Yeah, we have a few companies on the market using our solar cell indoor situation. We of course have made a lot of internal measurements and what type of light intensity you can expect in an indoor situation. This varies a lot, but in general we have data of what to expect in an office, what to expect in a home, what to expect in a store, for instance, in retail environment. So those data we have, which are general, but they're quite big spread. Then we have our customers that have products on the market for a while, and they have a lot of data which we don't have direct access to. At least we cannot share. But that is the type of information we have. So in general, when doing a product like this, an IoT product with indoor light, you need to do some work on finding a good power balance. And that power balance is based on the general environment that the customer will have this, or in many cases also real data from the customer that they know that in this environment we will have approximately this kind of light. And then you don't need to design the system so that it will be sustainable in terms of power over time.
And then, I mean, we have a number of products out in the field also working. So I think that is also one way to sort of show that it works also in real life applications.
So what technical considerations are important when integrating this, indoor solar cells with electronic devices? And how do you ensure seamless integration?
Yeah, it's a big topic. You have the electrical part, of course, that makes sure that this, most of the electronics, most of the IoT products today are designed to be run with batteries. And so, or solar cell in general doesn't work as a battery, so you need some electronics to make that work. So that needs to be considered, what kind of electronics is needed. And then you have the mechanics, of course. An IoT product designed for batteries has one form factor, and one that is designed for a solar cell has another. So usually we can make thin products but with a larger area that could of course be used for capturing the energy. And also our solar cells are not a typical electronic components. It's a thin film that should be integrated. So those are the things that need to be addressed. How is it mechanically integrated? What kind of electronics components needed? And also, of course, the energy storage, because you also always need an energy storage in this system so that it works during night, for instance, when there's no light. So these are the things that need to be considered.
Okay. So are there any specific requirement or standard that your cell meets to facilitate integration with various electronic products?
The requirements, the major requirements, of course, that it should run, it should work, it should be a power balance, it should have enough energy in to allow for the energy consumed in the device. That's of course quite obvious. But there are also other things to consider, and that is how quickly can it start up from you taking out of the box, or you have commissioning procedure for your device if there's a device that is important. And then other requirements will usually be around cost, and then the total cost of ownership is usually what is referred to. How do we make sure that this system is then better in some way than using a battery? A battery need to be replaced and so on. And then the environmental aspect is also the requirements. And then, as Jonas said, we have shown very good environmental properties of our technology, but then the system as a whole should be better than using a battery then.
So what does your company plays a role in integration solar cells with the ultra low power microcontroller? So how it happens, how you integrate the solar cells with ultra low power microcontrollers?
Yes. So there have been a convergence, both as Jonas said, that we have a technology, a solar cell that can work indoor and can harvest all the energy we have indoor, especially in very, very low light situation. So then the convergence in that performance, and then the ultra low power microcontrollers that have been going down in power draw. So that is a sort of you meet there at some point where it becomes feasible to do these indoors, so have these IoT sensors, very low power IoT sensors indoor. So that is sort of what's been happening, and it's happening then right now. And so the challenge right now is to sort of have this ultra low power electronics and to make them more suitable, or more, how should I put this, so that they work with a solar cell and not a battery, because a battery and solar cell have different behavior at startup and stuff like that. So that is sort of the current challenge, and that's what our work with the ONU then come into play.
So also you talked about that some energy storage system is also required when there is no light. So how it works? I mean, when there is no light, how the microcontroller will work?
So as Jonas said, we deliver maybe our standard module 50 by 50 deliver maybe 500 microwatts at normal indoor, normal office environment, which translates to maybe 150 micro amps, and all these microcontrollers will consume much less than this on average, but have much higher peak currents. So there need to be some reservoir. So even if you have a device that will only work when there's light, when you shine light on it, it still needs some reservoir. And then you need a small reservoir, maybe just a capacitor, fairly big capacitor, but still just a capacitor. And then you have the situation when you have something, maybe a temperature sensor or similar, you want it to work during night or maybe a weekend or so. Then you need a little bit larger storage element of some sort. A supercapacitor, for instance, is very common in that situation. Then you want this to work even during a long holiday, or even long dark periods or whatnot. Maybe you may look at seasonal changes. That is of importance. Then you need bigger storage, and then usually you go for a rechargeable battery. Still a very small rechargeable battery, but that's what you need then. Or even in some cases, these hybrid capacitor, which is a hybrid between a battery and a supercapacitor. That are the type of storage elements that is we see mostly today. And then there is coming technologies like printed batteries, like solid state batteries and things. There's a lot of things happening on that space at the moment. But the current ones are supercapacitors, hybrid capacitors, and small rechargeable batteries.
Okay, so right now you're providing a solution which also have the reservoir, the energy storage system. Is it like that?
Yes, well, our core competencies are solar cell, and that's what we provide. But enabled to make this to make the technology to make it happen, to make IoT companies out there to adopt energy harvesting, we need to at bare minimum have the knowledge to tell them how to do it, and in many cases we make complete sort of system proposal for them, which includes our solar cell, some ways to store the energy into the storage element, and sort of provide that as a system solution. However, we don't sell this system solution. We sell our solar cell, but we point to you should do this implementation.
From a technical standpoint, what considerations should manufacturers keep in mind while integrating indoor solar cells with their electronic devices?
The manufacturing, well, most manufacturing that do IoT products today are quite used to components that can be soldered in SMTs, soldered in reflow and wave soldering and stuff like that, and then have fairly easy connectors and so forth. Our product comes from a sphere of thin film and printed electronics, so it's a bit different. So there we have been working with the industry quite a lot to sort of find good ways to, for instance, solder our components to a board, or glue our component to a board, and also integrated in mechanical parts in a good way. So we need to sort of help the industry to do that, and then at some point it becomes a commodity product and then industry can do it themselves. But currently we need to support a lot there.
So what measures have you taken to ensure the durability and longevity of your indoor solar cells, especially in the environment where there is a variable lighting condition?
I mentioned before, also in the production, what we do with each production batch is that, of course, we do long-term accelerated aging tests. We do damp heat, climate chambers, ovens, light soaking, so where we have high light intensity over a long period of time, both continuous and intermittent, turning these higher light intensities on and off to try to accelerate the amount of photons or water molecules or temperature that the modules are exposed to. Also, since the product release, I think this was about 3 years ago, we have a lot of modules also placed up on walls here in the office, where we can see that they perform consistent and reliable, and they don't degrade especially fast. So from that perspective, I think we are in a quite good position.
So can you provide an overview of the current competitive landscape in indoor solar cell industry, including key competitors and their offerings?
Yeah, I mean, so for indoor solar cells, I would say that right now it's mainly pushed by companies working with organic solar cells, so polymer based like ours, or Grätzel solar cells from a maturity perspective. Then you also have a bunch of companies working on perovskite solar cells. It looks like they are a few years behind, but performance wise it looks really promising. You have some company working with gallium arsenide solar cell, which is a really high performance material, but drawback is that it usually costs quite much. Then of course you have the manufacturers of amorphous silicon in different places of the world as well. So I would say that this is probably the sort of main technologies.
So how does your company differentiate itself from the other companies in the same market?
So I think it's the flexibility of our solar cell. It's a reliable and high performance, and at the same time at what we hope at least a good cost picture as well for the solar cells. We can offer both single cells for quite nice looks, and we can also offer series connected cells where we then can adapt the voltage output of the solar cell to the levels required then by the electronics to power.
So are there any specific technical benchmark that demonstrate the superiority of your company with the competitors?
In terms of, I mean, if you look at, I mean, there's a number of aspects you need to consider. So I mean, if you look at purely the power conversion efficiency, typically the companies working with the gallium arsenide have the highest power conversion efficiency. And then you need to look at, do you want something that's rigid? Do you want something that's flexible? Do you want to be able to tune the voltage output of your solar cell? What is the cost level you can accept? It's a number of aspects that you need to consider then when you select your supplier of solar cells.
Okay, so is there any ongoing research and development efforts that you're undertaking to improve the performance, efficiency, or cost effectiveness of the indoor solar cells?
Yeah, also there, like I mentioned before, this change of the active layer from fullerene or polymer fullerene based into a polymer non-fullerene is sort of the main route towards increasing the power conversion efficiency or power density. And then in terms of cost, there is, of course, making the production process more efficient, reducing the waste. And then there is a few of the material components that we are looking into negotiations in the cost for sort of the suppliers, or maybe looking at different suppliers then to try to see what is possible to do there. But I would say that also with scale and volume, of course, cost is going down.
So how do you stay updated with the latest advancement in materials and technology that can benefit your product?
Trying to participate in academic conferences, I would say, and keeping the outreach and discussion with the people active in the field.
So how does your company address issues related to scalability and mass production of solar cells to meet the demands of IoT device manufacturers?
Yeah, like I said, the roll-to-roll production process, I think, is the choice of using roll-to-roll manufacturing and printing and coating is our way to handle this, as it allows for very high volumes.
So what are the different applications apart from the IoT devices? What are the different applications in which the indoor solar cells are used?
You can look at, for instance, remote controls, electronic shelf labels, so a number of different areas, I would say. Also a bit of consumer electronics is typically where indoor solar cell tend to end up. Quite nice products out on the market for what do you call it? Earphones. And other what can it be? Keyboards, mouses.
Basically any product which is indoor and has a battery that's a small battery, a low power product indoor can benefit from this.
Okay, so they can benefit from this, right? But are you having such clients which are making earphones or making mouse?
No, not out on the market. There is other companies that has products out on the market here. Then of course we are in discussions with different aspects, and I would say right now we focus very much on the IoT connected devices. But of course, we are looking into other markets as well. For instance, electronic shelf labels is, of course, very interesting to us.
So are there any technical strategies in place to reduce the production cost while maintaining the quality? So can you discuss any technical strategies?
Yeah, I mean, like I said before, it is looking at the different materials. And of course, seeing what we can do with those to reduce the cost of each component that's used in a solar cell.
So now I have my last question in the line. So in terms of manufacturing, what are the key factors that contribute to the scalability and efficiency of indoor solar cell production process, complete production process?
So I would say it's basically the roll-to-roll manufacturing, where we use roll-to-roll printing to print the current collectors. We use roll-to-roll slot die coating to build a solar cell and construct the solar cell. And then we use roll-to-roll conversion to convert, and this conversion process is basically then going from the roll and into single pieces. We also have a roll-to-roll process that we have developed to adhere barrier foils, because organic solar cells are sensitive to oxygen and moisture. And then also in this roll-to-roll process, we apply these encapsulation foils and barriers, and then we cut the modules out from these foils in the end. So it's a full roll-to-roll process, then starting with bare PET all the way into sort of the cutout encapsulated module.
Okay. So, one more question I have. So, apart from these ultra low power microcontrollers with which you are collaborating, there are any other companies with which you have collaborated? You are giving your indoor solar cells, any other IoT device or any other electronic device which is using this as of now?
I'll say yes. We are exploring the space of energy harvesting in IoT from all aspects. I mean, the ultra low power microcontroller is one, but also all the electronic components needed to harvest energy into a storage is another one, where there's a lot of companies and active. We also, of course, collaborate a lot with the storage, the companies that provide storage of different kinds. That's typically the main areas where we do a lot of collaborations, but also to some extent with the end producers of components to sort of drive the market forward. So we collaborate in a broad field, the entire field of energy harvesting. I'd say we try to collaborate.
Okay, so talking about the ultra low power microcontroller only. So in that particular thing, the contribution is the solar cell, not the energy storage system, or
No.
both from your end.
Yeah, I mean, it's the in this particular collaboration, or it's a solar cell.
Okay.
And the ultra low power microcontroller in this case is one that is designed with energy harvesting in mind. So that's why it's interesting for us then. And so it's a dual way thing here. They need to understand how they best can have a microcontroller that works with a solar cell and that we can provide information on. And also we benefit from having these kind of products that are sort of designed for energy harvesting from scratch and not for batteries, because it's make a better fit and it makes better end products in the end.
Okay, so I think I'm done with all my questions. So great, it was great talking to you. Thanks for taking your time out.